Right now, 1200 light-years from where you are sitting, a planet more than twice the width of Jupiter is bleeding into space. Not slowly, not imperceptibly. At this precise moment, as you read these words, approximately 10 million metric tons of atmosphere are streaming away from that world every single second. The gas does not drift aimlessly. It pours outward in a coherent stream sculpted by orbital mechanics and stellar gravity into a ghostly tail of helium that stretches ahead of the planet in its orbit, a tail extending more than 130 times the planet's own width, across the void. If you could see it with your naked eye from Earth, that tail would be one of the largest visible structures in the night sky. You cannot see it. You are 1200 light-years away. And even at that distance, the signal is strong enough to register on our instruments, unmistakable, undeniable, a planet announcing its own destruction to anyone patient enough to look. The planet is called HAT-P67b. It is one of the largest planets ever confirmed by science. Its radius measures more than 2.14 times the radius of Jupiter, making it wider than any world in our solar system by a factor that defies easy comprehension. If you placed it next to Jupiter, it would dwarf the king of our solar system the way Jupiter dwarfs Earth. Its volume is roughly 10 times that of Jupiter. If our solar system's largest planet is a basketball, HAT-P67b is a beach ball placed beside it. But here is what no one tells you when they hand you that number. Here is the fact that breaks everything you assumed about what the largest planet would be. HAT-P67b, despite being more than twice as wide as Jupiter, weighs less than half as much. Its mass is approximately 0.45 Jupiter masses. Its density is 0.061 grams per cubic centimeter. For reference, water sits at 1 gram per cubic centimeter. Jupiter sits at 1.33. Saturn, the least dense planet in our solar system, still manages 0.69. A marshmallow, the soft, insubstantial confection you can crush between two fingers, has a density of roughly 0.1 to 0.15 grams per cubic centimeter. HAT-P67b is less dense than a marshmallow. This is not a typo. This is not a measurement error. This has been confirmed by multiple independent research teams using multiple instruments across more than a decade of observation, culminating in a 2025 study published using the NEED spectrograph at Kitt Peak National Observatory that produced the most precise mass measurement this planet has ever received. The largest planet is not the strongest planet. It is not the heaviest. It is not the most gravitationally ferocious. It is one of the most fragile objects that has ever earned the name planet, and it is currently dissolving. This is the story of what happens when physics is pushed to its absolute limit. When a world is placed so close to its dying star that the same energy keeping it inflated to record-breaking dimensions is simultaneously tearing it apart. When the largest becomes the most temporary. When the word planet stops, meaning what you thought it meant. If you find yourself drawn to stories that shatter your assumptions about what the universe is capable of building and then show you exactly how it destroys what it builds, do me a small favor and hit that like button and subscribe. It genuinely helps this channel continue, and there are more stories like this one waiting. Get yourself comfortable. Let's begin. Close your eyes for a moment and build the largest planet in the universe inside your mind. Whatever your imagination constructs, it is wrong. But the specific way it is wrong tells you something important about how humans understand scale power and what it means for something to be large. You almost certainly imagined something heavy, something with gravity so ferocious it would flatten a spacecraft in seconds. A world of crushing atmospheric pressure, violent storms, and radiation so intense that nothing biological could survive within 10,000 kilometers of its cloud tops. You imagined, in other words, a bigger Jupiter. That instinct is not random. It follows from everything we know about the largest planet in our own solar system, and Jupiter earns every superlative we give it. It is 11 times wider than Earth. You could fit more than 1300 Earths inside its volume, and still have room remaining. Its mass is 318 times that of our planet. It weighs more than every other planet, moon, asteroid, and comet in the solar system combined, and then doubles that figure for good measure. Jupiter is not merely the largest thing orbiting our sun. It is the gravitational anchor around which the entire architecture of our solar system was organized. Stand on Jupiter's cloud tops if you could somehow survive the environment, and you would weigh 2.5 times what you weigh on Earth. The atmospheric pressure beneath those clouds climbs to levels that would crush a nuclear submarine in seconds. Winds scream at 350 miles per hour. The Great Red Spot, a storm that has been raging for centuries, is large enough to swallow Earth with room to spare. Lightning bolts in Jupiter's atmosphere release energy 1,000 times greater than terrestrial lightning. The radiation belts surrounding the planet are intense enough to deliver a lethal dose to an unshielded human in minutes. Jupiter's gravitational reach extends so far that it has captured 95 known moons, several of which would qualify as significant worlds in their own right. Ganymede, the largest of them, is bigger than the planet Mercury. Europa hides a global ocean beneath a shell of ice that may contain more liquid water than all of Earth's oceans combined. Io, stretched and squeezed by tidal forces from Jupiter, and its sibling moons erupts with volcanic fury unlike anything else in the solar system. With plumes reaching hundreds of kilometers into space, Jupiter also plays a role in the history of life on Earth that we are only beginning to appreciate. Its massive gravity has over billions of years deflected comets and asteroids that might otherwise have bombarded the inner solar system with far greater frequency. Some researchers believe that the existence of a gas giant in the outer solar system is one of the preconditions for complex life on a rocky inner world to have enough time to evolve without being periodically reset by catastrophic impacts. Jupiter did not merely build our solar system, it may have protected the conditions that made us possible. This is the template your mind uses. Largest means most massive, largest means most powerful, largest means most gravitationally ferocious. The relationship seems obvious, even inevitable. In nearly every domain of human experience, size and substance scale together. Larger elephants are heavier, taller buildings contain more steel, bigger stars are more massive. When things grow, they accumulate. Mass and volume move in the same direction. For centuries, this principle held firm in planetary science. The planets of our solar system obeyed it with satisfying consistency. The rocky inner worlds were small and dense. Earth, the largest of them, measured roughly 8,000 miles across, with a density 5.5 times that of water. The gas giants of the outer solar system were large and less dense, but still impressively massive. Jupiter sat at the top, biggest and heaviest. The correlation seemed like a law of nature. Then astronomers pointed their telescopes at other stars, and the law dissolved. The first confirmed exoplanet orbiting a sun-like star was detected in 1995. Michel Maire and Didier Queloz, working at the Observatoire de Haute-Provence in southern France, used the radial velocity technique to detect a world orbiting the star 51 Pegasi. The discovery earned them the Nobel Prize in Physics in 2019, and it deserved that recognition. Not merely because finding a planet around another sun was itself extraordinary, but because of what kind of planet they found. 51 Pegasi b was a gas giant, roughly half the mass of Jupiter. That was not the shocking part. The shocking part was its orbital period, 4.2 days. It was circling its star faster than Mercury circles, our sun orbiting at a distance far closer to its star than our innermost planet ever gets. Nobody expected this. The models of planet formation developed over decades of careful theory said that gas giants should form in the cold outer regions of planetary systems far from their parent stars, where ices could accumulate into massive cores capable of pulling in vast envelopes of gas. Finding a gas giant practically touching its star was, to use the analogy that quickly became standard in the field, like finding a snowman standing undisturbed in a blast furnace. The discovery opened the floodgates. Within a few years, dozens of similar planets were found, giant worlds on scorching tight orbits. They earned a nickname that immediately captured what made them strange hot Jupiters. And as the catalogue of hot Jupiters grew, an uncomfortable truth began to emerge. The relationship between planetary size and planetary mass was far more complicated than anyone had assumed. Some hot Jupiters were heavier than Jupiter, but roughly the same width. Others were lighter than Jupiter, but noticeably wider. A few were significantly wider than Jupiter, while carrying only a fraction of its mass. The neat correlation that seemed like a universal law was a local coincidence, a quirk of our own solar system's specific history. The exoplanet catalogue continued to grow, driven by increasingly sophisticated detection methods. Transit photometry, where astronomers measure the tiny dimming of a star as a planet crosses in front of it, allowed precise measurements of planetary radii. When combined with radial velocity measurements of planetary mass, astronomers could calculate something they had never before been able to measure for distant worlds' density. And the densities were deeply strange. Some gas giants had densities comparable to Jupiter. Others registered densities so low they initially seemed like measurement errors. Planets with the volume of Jupiter but less mass than Saturn. Worlds with the width of a giant planet but the substance of something closer to heated fog. These were the inflated hot Jupiters. Planets puffed up to dimensions that their mass alone could never explain. Standard models of planetary structure predict that a gas giant of a given mass and age should contract to a specific radius as it cools over billions of years. For cold gas giants far from their stars, the models work beautifully. For planets on tight orbits bathed in intense stellar radiation, the models consistently underestimated how large the planets actually were. The planets were too big, not by a small margin, by 20, 30, sometimes 50% or more, sometimes by factors that could not be explained by any single adjustment to the models. The question of what was making these worlds swell beyond their predicted sizes became one of the central problems of exoplanet science. Dozens of mechanisms were proposed, hundreds of papers were written, the debate continued for years, and in some respects, continues today. What became clear, even as the details remained contested, was that proximity to a star fundamentally transforms what a gas giant can be. A gas giant in the cold outer reaches of a planetary system forms, cools, contracts, and settles. A gas giant orbiting a fraction of an astronomical unit from a luminous star never settles. It is perpetually disturbed, perpetually inflated, perpetually prevented from becoming the compact, predictable object that physics would otherwise produce. And then there is HAT P67b, a planet that does not merely sit at the inflated end of the distribution, a planet that occupies a corner of the mass-radius diagram so extreme that almost nothing else survives there. A planet that is not the heaviest, not the densest, not the most gravitationally powerful world in the catalogue, but is perhaps the most physically swollen, most grotesquely oversized, most structurally fragile object that has ever been, confirmed as a planet, a ghost in the shape of a world. Finding it required patience, precision, and instruments so modest that most people would walk past them without a second glance. And what those instruments found in a star field in the constellation Hercules has been unsettling planetary scientists ever since. The Hungarian Automated Telescope Network does not sound like the kind of instrument that changes our understanding of the universe. The name conjures images of grand observatories perched on mountain summits of gleaming primary mirrors the size of tennis courts of billion-dollar spacecraft drifting silently above the atmosphere. HatNet is none of these things. Its telescopes have apertures of just 11 centimeters, roughly the diameter of a large coffee can lid. They are modest, automated, and almost entirely unattended. They sit at two sites, one at the Fred Lawrence Whipple Observatory on Mount Hopkins in southern Arizona, the other on the summit of Mauna Kea in Hawaii. And together, watching hundreds of thousands of stars simultaneously night after night, they found one of the most extreme planets ever confirmed. The technique they use is conceptually simple, almost elegant in its directness. When a planet orbits a star in a plane aligned with our line of sight, it periodically crosses in front of the stellar disk as seen from Earth. During that crossing, the planet blocks a small fraction of the starlight reaching us. The star dims almost imperceptibly for a few hours. Then the planet moves on, and the brightness returns to normal. If this dimming occurs repeatedly at regular intervals, it is almost certainly caused by something orbiting the star. The depth of the dimming tells you how large the transiting object is relative to the star. The interval between successive dimmings tells you the orbital period. This technique is called transit photometry, And it is the reason we have confirmed thousands of exoplanets that no other method could have found. HatNet began monitoring the star, now designated HAT P67 inches 2005. Additional observation campaigns followed in 2008. The data accumulated slowly, the way all patient science does, night by night, transit by transit, each dimming adding another data point to a pattern that was gradually becoming too regular to dismiss. The periodic dips in the star's brightness were consistent with a large object transiting every 4.81 days. The depth of those dips suggested something enormous was crossing the stellar disk, something considerably wider than Jupiter. But a transit signal is not a planet. This is a point that exoplanet scientists emphasize with the weariness of people who have made the same correction many times. Several astrophysical scenarios can produce a periodic dimming that looks identical to a planetary transit. A faint background eclipsing binary two stars orbiting each other blended with the light of the target star can mimic the signal perfectly. A brown dwarf, an object too massive to be a planet, but too small to sustain the hydrogen fusion that defines a true star, can also transit and produce comparable signatures. Ruling out these alternatives requires measuring the mass of the transiting object, and measuring mass requires a completely different kind of observation. The standard method is the radial velocity technique. As a planet orbits its star, the planet's gravitational pull induces a subtle wobble in the star's motion. This wobble causes the starlight to shift toward bluer wavelengths when the star moves toward us, and toward redder wavelengths when it moves away. By precisely tracking these spectral shifts over time, astronomers can determine the mass of the orbiting body. The technique is extraordinarily sensitive. Modern spectrographs can detect stellar wobbles corresponding to velocities of less than 1 meter per second slower than a person walking at a casual pace. The radial velocity method has confirmed hundreds of planetary companions and remains the most reliable way to turn a transit signal into a confirmed planet with a measured mass. HAT P67, however, is a deeply uncooperative star for this kind of measurement. It is an F-type subgiant, a star somewhat hotter and larger than our Sun, and it rotates at a projected velocity of nearly 36 kilometers per second. For comparison, our Sun rotates at roughly 2 kilometers per second. HAT P67 spins approximately 18 times faster. This rapid rotation does something devastating to the precision of radial velocity measurements. It broadens every spectral line in the star's spectrum, smearing the sharp features that spectrographs depend on into wide, shallow, difficult-to-measure curves. The subtle wobble induced by a planet of less than 1 Jupiter mass, the tiny gravitational tug of a relatively low-mass companion, simply drowns in the noise created by the star's own rotational blur. Early radial velocity observations carried out at the Keck Observatory between 2009 and 2012 could not establish a definitive mass for the transiting object. They could only set an upper limit. Whatever was crossing in front of HAT P67 weighed less than 0.59 Jupiter masses. That finding was enough to rule out a stellar companion or a massive brown dwarf, both of which would produce wobbles far larger than anything detected. But between a small fraction of Jupiter's mass and 0.59 Jupiter masses lies an enormous range of possibilities. The difference between those extremes is the difference between a modest gas giant and something approaching the mass of Saturn. Without a precise measurement, the planet's density, interior structure, and evolutionary fate could not be determined with any confidence. The team turned to a more subtle technique. Doppler tomography does not attempt to measure the star's overall radial velocity shift. Instead, it tracks how the planet's shadow moves across the rotating stellar disk during a transit. Because different parts of the star's surface are moving toward or away from us at different velocities due to the rotation, the light blocked by a transiting planet carries a specific velocity fingerprint depending on which part of the disk the planet is currently crossing. By watching how this blocked velocity signature evolves over the course of a transit, astronomers can distinguish a genuine compact transiting body from a blended background binary, which produces a different and identifiable pattern. Two separate Doppler tomographic detections of HAT P67b's transit were obtained, each confirming the signal as a real planetary companion crossing a real stellar disk. The observations also revealed something important about the planet's orbital geometry. The planet's orbit is aligned with the spin of its host star to within roughly 12 degrees in projection. This near alignment carries a story about how the planet arrived at its current position. Planets can migrate inward from their formation sites in the outer planetary system through two very different mechanisms. The first is smooth, gradual migration driven by interactions with the protoplanetary disk, the vast cloud of gas and dust from which the planetary system forms. As the young planet orbits within this disk, gravitational interactions between the planet and the disk material transfer angular momentum, causing the planet to spiral slowly inward over millions of years. This process tends to preserve the alignment between the planet's orbit and the star's equatorial plane, because the disk itself orbits in the same plane as the star's rotation. The second mechanism is far more violent. A planet can be kicked onto an eccentric, tilted, or even retrograde orbit through close gravitational encounters with other massive planets, eventually settling into a tight circular orbit through tidal damping over long timescales. This process tends to produce misaligned orbits because the scattering events that initiate it are not constrained to occur in the orbital plane. HATP-67b's near-perfect alignment argues for the smooth disk migration scenario. This planet did not arrive at its current scorching orbit through violence. It drifted inward, gently carried by the viscous drag of the disk that surrounded its young star, following the track laid down by the gas and dust from which it formed. A later independent confirmation using the Rossiter-McLaughlin effect at the Galileo National Telescope determined the projected spin-orbit angle to be just 2.2 degrees. 2 degrees. For all practical purposes, this planet orbits in the same plane as its star's equator, as obediently as if it had never moved at all. The discovery paper, led by George Zhou and colleagues, was published in 2017 Inches, the Astronomical Journal. It reported a radius of approximately 2.085 Jupiter radii, enormous, immediately placing HATP-67b among the largest radius exoplanets in the catalogue. It reported the mass upper limit of less than 0.59 Jupiter masses. And it reported what those two numbers taken together implied about the planet's density. Even with only an upper limit on the mass, the density was already strikingly low. If the planet weighed anywhere near its maximum allowed mass, its density would be below 0.1 grams per cubic centimeter. If it weighed significantly less, the density would be lower still. The paper identified HATP-67b as among the lowest density gas giants known, a world of staggering dimensions and astonishing insubstantiality. But science is not satisfied by upper limits. For nearly 8 years after that discovery paper was published, the actual mass of HATP-67b remained unmeasured. Various teams studied the planet's atmosphere, detecting extraordinary chemical signatures we will return to in detail. Hubble Space Telescope observations probed the structure of its outer layers. Theoretical models attempted to explain how any planet could have grown so large. But the fundamental question, how much does this planet actually weigh, resisted every attempt to answer it with precision. The host star's rapid rotation continued to defeat conventional radial velocity campaigns. Every team that tried to measure the mass ran into the same wall of noise. Then, in 2025, a team led by Gavin Wang published a study that changed everything. They used the NEED spectrograph installed on the WIN 3.25-meter telescope at Kitt Peak National Observatory, a next-generation instrument designed with extreme precision in mind. But the instrument alone was not sufficient. The team had to overcome a problem that made the mass measurement uniquely difficult, even by the standards of rapidly rotating stars. They discovered that HATP-67's rotation period of approximately 5.4 days sits remarkably close to the planet's orbital period of 4.81 days. This near synchronization created a dangerous ambiguity. Stellar activity signals the spectral distortions produced by star spots, magnetic regions, and surface convection rotating in and out of view occur at the star's rotation period. When that period nearly matches the planet's orbital period, the stellar noise becomes almost indistinguishable from the planetary signal. The two frequencies interfere with each other, potentially producing false signals or masking real ones. To disentangle them, the team employed a statistical technique called a constrained quasi-periodic Gaussian process. This is a method for modeling correlated noise, the kind of noise that repeats with a characteristic timescale rather than occurring randomly, and separating it from the coherent, precisely periodic signal produced by an orbiting planet. They combined new need radial velocity observations with archival ground-based photometry and space-based photometry from NASA's Transiting Exoplanet Survey satellite, known as TESS. The multi-wavelength dataset allowed them to characterize the stellar activity independently and subtract its contribution from the radial velocity signal, leaving behind the planetary signature with unprecedented clarity. The result was a number that had eluded planetary scientists for 8 years, a mass of 0.45 Jupiter masses with an uncertainty of plus or minus 0.15 Jupiter masses, combined with a refined radius of 2.14 Jupiter radii derived from the same dataset. This produced a density of 0.061 grams per cubic centimeter, the second lowest density ever measured for a confirmed hot giant planet, a density so remote from anything in our solar system that the comparison to a marshmallow, which sounds like an absurdity, is in fact generous. A marshmallow is denser. To appreciate just how extraordinary that number is, it helps to build it in your mind rather than simply reading it. Imagine you have a container exactly the size of Jupiter. You fill that container not once but 10 times over. HATP67b has roughly 10 times Jupiter's volume. Now, imagine that all the material you pour into those 10 Jupiter-sized containers weighs less than half of what Jupiter itself weighs. The density of the resulting object is what you see inside that container, not a planet in any familiar sense, not a world of crushing pressures and fierce gravity, something closer to an enormous warm cloud, a diffuse concentration of hydrogen and helium, so thin at its outer edges that the boundary between planet and surrounding space becomes, in the most literal physical sense, impossible to define with precision. And this cloud of nearly nothing, this planetary ghost, is orbiting its host star at a distance of just 0.065 astronomical units. That is approximately 10 million kilometers. Mercury, our solar system's innermost planet, orbits our sun at roughly 58 million kilometers. HATP67b is nearly 6 times closer to its star than Mercury is to ours. Its year lasts 4 days and 19 hours. While Earth completes a single orbit around the sun, this planet circles its star 76 times. It moves through space at roughly 130 kilometers per second, more than 4 times faster than Earth moves in its orbit. The environment this planet inhabits is not merely hostile, it is actively and continuously lethal to the kind of structure a planet is supposed to maintain. And the star itself is not a stable patient companion. HATP67 is 1.73 times the mass of our Sun and 2.65 times its width. It is roughly 12 times more luminous. And it is not on the main sequence, the stable hydrogen-burning phase, that defines most of a star's life. It is a subgiant, a star that has begun to exhaust the hydrogen fuel in its core and is starting to evolve toward the red giant phase. It is brightening. It is swelling. The radiation environment it creates around its close orbiting companion is not static. It is intensifying year by year, century by century, with the slow but inexorable momentum of stellar evolution. For HATP67b, this means the killing has already begun. But the nature of that killing, the specific physical mechanisms by which a planet more than twice the width of Jupiter is being systematically stripped of its own atmosphere and returned to the void, is a story that requires understanding something deeper first. It requires understanding how this planet became so large in the first place, because you cannot understand why it is dying without first understanding what made it possible. What comes next takes us inside the planet itself, into the physics of inflation, the mechanisms by which a world of ordinary ingredients is stretched to extraordinary dimensions, and into the reason why the very force that created this record-breaking object is the same force that is now destroying it. 1705, Claude responded. To understand how HATP67b became what it is you need to begin with, what a gas giant is supposed to do over the course of its life. To understand how HATP67b became what it is you need to begin with, what a gas giant is supposed to do over the course of its life. Not what it looks like from the outside, not the storms and the bands and the magnetic fields, but the deeper thermodynamic story. The story of what happens to a ball of hydrogen and helium over billions of years when left to its own devices in the cold dark of space. Gas giants are born hot. This is not a metaphor. The gravitational energy released during planetary formation, the energy of countless collisions of infalling material, compressing against itself of a protoplanetary core, accumulating mass at rates that would be incomprehensible on any human timescale, heats the nascent planet to temperatures of thousands of degrees. A newly formed gas giant glows with this residual heat. It radiates infrared light into space. It is, in a meaningful physical sense, a small failed star cooling toward equilibrium with its surroundings. Over time, that cooling proceeds. The planet radiates energy outward. Its interior temperature drops. As it cools, it contracts. The gas that had been maintained at high temperature and correspondingly high pressure settles inward under the pull of gravity. The planet shrinks. Not rapidly in any human sense, the process takes hundreds of millions of years, but steadily and predictably, driven by the thermodynamic imperative that every hot object eventually cools to match the temperature of its environment. Given enough time, the planet reaches a configuration where the outward pressure of its compressed interior gas and the quantum mechanical resistance of degenerate electrons exactly balance the inward pull of gravity. The radius at this equilibrium depends almost entirely on the planet's mass and composition. It is for a cold, isolated gas giant essentially determined. Jupiter illustrates this beautifully. At roughly 4.5 billion years old, it has had time to cool and contract nearly to its equilibrium radius. Models suggest it was perhaps 30 to 40% larger when it first formed. It will continue to shrink imperceptibly over the billions of years ahead, following the cooling curve that the physics of degenerate hydrogen dictates. Give an astronomer Jupiter's mass, its age, and its composition, and they can predict its radius to within a few percent. The system is well understood. The physics is clean. Now, change one variable. Take that same ball of hydrogen and helium and move it to within 10 million kilometers of a luminous star. Everything changes. Not because the laws of physics change. The laws are identical everywhere, but because the boundary conditions change so dramatically that the same laws produce a completely different outcome. At 10 million kilometers from a star 12 times more luminous than our Sun, the planet's dayside is being irradiated with an intensity roughly 200,000 times greater than Earth receives from the Sun. The energy flux striking the planet's atmosphere is so enormous that it fundamentally overwhelms the planet's own cooling mechanism. The planet is trying to radiate heat outward. The star is pouring far more heat inward. The planet cannot cool, it cannot contract. It is trapped in a state of perpetual thermal inflation, prevented from reaching the compact equilibrium that physics would otherwise demand. But here is where the story becomes more subtle and more scientifically contentious. Simply warming the outer atmosphere is not by itself sufficient to inflate the planet's overall radius significantly. The visible atmosphere of a gas giant, the layers we can observe, directly represents only a tiny fraction of its total mass. Warming that thin outer shell changes the planet's appearance and its spectral properties, but it does not substantially alter the planet's bulk structure. To inflate the planet's radius, to actually push the whole object outward against its own gravity energy, must penetrate much deeper. It must reach the inner regions where the bulk of the planetary mass resides, at pressures of hundreds or thousands of times Earth's atmospheric pressure at sea level, where the gas behaves less like a familiar fluid and more like the planetary mass treat, compressed exotic states of matter that exist nowhere else in our ordinary experience. This is the central puzzle of hot Jupiter inflation. The energy is arriving at the atmosphere. The planets are demonstrably larger than they should be. Something is transporting that energy from the surface layers into the deep interior. But what the mechanisms proposed to explain this transport have been debated for more than 2 decades, and the debate has generated some of the most technically sophisticated work in modern planetary science. The first and most widely discussed mechanism is called ohmic dissipation. The concept begins with ionization. In the atmosphere of a planet like HATP67b, subjected to temperatures approaching 2000 Kelvin and flooded with ionizing radiation from its host star, alkali metals such as sodium and potassium become partially ionized. Electrons are stripped from atoms and drift freely through the atmospheric gas. The result is a partially conducting medium, not as conductive as a copper wire, but enough to sustain electrical currents under the right conditions. Those conditions exist here. The planet has a magnetic field generated in its interior through the same dynamo processes that produce Jupiter's magnetic field, though in HATP67b, the field is likely weaker due to the planet's lower density and correspondingly different interior structure. The powerful winds that blow across the planet's atmosphere, driven by the enormous temperature difference between the scorching day side and the cooler night side, carry this ionized gas across magnetic field lines. Moving a conductor through a magnetic field generates an electrical current. The current flows through the deeper, more resistive layers of the planet's interior. Where it encounters resistance, it deposits heat. Ohmic heating, the same physical process that makes a light bulb filament glow, warms the interior. The appeal of ohmic dissipation is its self-consistency. The mechanism is driven by stellar irradiation, which means more irradiated planets should experience more inflation, which is precisely what the population of observed hot Jupiters shows. Statistical studies of hundreds of hot Jupiters have confirmed that the degree of inflation correlates with the level of incident stellar flux in a way that ohmic dissipation models predict reasonably well. Research by Daniel Thorngren and Jonathan Fortney, analyzing a large sample of hot Jupiters, found that the functional form of the inflation efficiency required to match the observations most closely resembles what the ohmic dissipation framework produces, including a decrease in efficiency at the very highest temperatures, where the atmosphere becomes so thoroughly ionized that it short-circuits the currents before they can carry energy deep enough to matter. But ohmic dissipation has limitations that its proponents acknowledge. Some calculations suggest the mechanism may not be powerful enough in absolute terms to explain the most extreme cases of inflation. The depth at which ohmic currents deposit their energy is relatively shallow near the boundary between the planet's radiative and convective layers, rather than in the deep convective interior, where energy would have the most leverage over the planet's overall radius. A 2025 study examining the internal luminosities of hot Jupiters found evidence suggesting that the deep interior contributes far less heat than models assuming deep central heating would predict, with intrinsic luminosities reduced by 95 to 97% compared to those models. This supports a picture in which the inflation is primarily driven by shallow heating deposited near the top of the convective zone rather than deep within it, consistent with ohmic dissipation or a similar mechanism. The planet is being inflated from the outside in, not from the inside out. The second mechanism is tidal heating. The physics here is more intuitive. If a planet orbits its star on an orbit that is even slightly elliptical, rather than perfectly circular, the gravitational pull it experiences from the star varies over the course of each orbit. When the planet is closer to the star, the pull is stronger. When it is farther, the pull is weaker. This varying gravitational force stretches and squeezes the planet with each orbit, flexing its interior the way you might flex a rubber ball by repeatedly deforming and releasing it. This flexing generates friction. Friction generates heat. The heat is deposited throughout the planet's interior, including at depth, making tidal heating in principle more effective at inflating the planet's overall structure than shallow atmospheric mechanisms. You have seen this process operating in our own solar system in one of the most dramatic ways the universe has found to make a point. Jupiter's moon Io, stretched and kneaded by gravitational forces from Jupiter and its sister moons Europa and Ganymede, is the most volcanically active body in the solar system. Its surface is constantly being reshaped by hundreds of active volcanoes. Plumes of sulfur dioxide reach hundreds of kilometers into space. the entire moon is in a meaningful sense being cooked from within by tidal forces. Tidal heating is real, it is powerful, and it operates at depth. For hot Jupiters, however, tidal heating faces a fundamental problem. The mechanism requires orbital eccentricity. A perfectly circular orbit experiences no variation in gravitational force over time and therefore generates no tidal flexing. And hot Jupiters, on very short orbital periods, tend to have very circular orbits. The same tidal forces that would generate interior heating also work to circularize the orbit over time, a process called tidal damping. For most hot Jupiters, tidal circularization occurs on timescales much shorter than the age of the system. By the time we observe these planets, the eccentricity has already been damped away. The mechanism that could inflate them has largely shut itself off. For HAT P67b specifically, the orbit appears nearly circular, limiting the contribution tidal heating can make to the planet's current inflation. Tidal effects may have contributed more substantially early in the planet's history, when the orbit was still circularizing, but that era is long past. The third mechanism operates through the atmosphere itself without requiring magnetic fields or orbital eccentricity. It begins with a well-established observation. Hot Jupiters develop powerful atmospheric circulation patterns driven by the extreme temperature contrast between their permanently illuminated day side and their permanently dark night side. Super-rotating jet streams form at the equator, carrying hot gas from the day side toward the night side at velocities that can reach several kilometers per second. General circulation models, sophisticated three-dimensional atmospheric simulations, have been used to study these wind patterns in detail, and they reveal something unexpected. The circulation does not simply redistribute heat horizontally across the planet's surface. It also moves air vertically. On the night side of the planet, where air flows downward after being carried around from the day side, the descending gas compresses and warms, but the warming happens along a steeper temperature gradient than one-dimensional atmospheric models assume. The result is that the deep atmosphere on the night side is hotter than simple calculations would predict. A hotter deep atmosphere is a less dense deep atmosphere. A less dense deep atmosphere means the planet's interior is maintained at higher entropy, a measure of the thermal disorder of the gas than it would be without the circulation. And a higher entropy interior is a more expanded interior. The planet inflates. This mechanism, called advective transport of entropy, or advective heat transport, requires nothing exotic, no magnetic fields, no orbital eccentricity, just the atmospheric circulation that any strongly irradiated, tidally locked planet would naturally develop. The difficulty is that modeling it accurately requires three-dimensional general circulation simulations of considerable complexity, and different research groups using different models have arrived at different conclusions about how much inflation advective transport can produce. Some find it sufficient to explain most of the observed inflation in typical hot Jupiters. Others find it inadequate for the most extreme cases. The debate remains unresolved, and it is likely that the true answer involves all three mechanisms: ohmic dissipation, tidal effects, and advective transport, operating simultaneously with different relative importance in different systems. For HAT-P67b, all three mechanisms may be contributing, but even together they are being stretched to their limits. The planet's mass of approximately 0.45 Jupiter masses places it in a range that population studies have identified as unusually susceptible to inflation. Research examining how the degree of inflation varies with planetary mass across the hot Jupiter population has found a striking pattern. Planets between approximately 0.37 and 1 Jupiter mass inflate more dramatically in response to stellar irradiation than either lighter or heavier planets. Below this range, planets simply do not have enough envelope mass to sustain large radii, regardless of how much energy is deposited. Above this range, the increased gravitational self-compression of the more massive planet resists inflation more effectively. The stronger gravity squeezes the gas harder, counteracting the tendency to expand. In the intermediate mass range, where HAT P67b sits, the planet's gravity is weak enough that even a modest amount of additional interior heating can drive enormous increases in radius. The gas inflates readily because there is not enough gravitational force to push back. This is the counterintuitive heart of why P67b is so large. It is not large because it is massive. It is large precisely because it is not very massive. Its own gravity is too weak to resist inflation. If you added mass to this planet, if you poured in more hydrogen and helium, you would not make it larger, you would make it smaller. The increased gravity would squeeze the existing material more efficiently than the new material added volume. The relationship between mass and radius for gas giants is not a simple upward curve. It rises, reaches a peak, somewhere around 1 to 2 Jupiter masses, under conditions of intense irradiation, and then turns over. The very largest radius planets belong not to the most massive objects, but to the most inflated, moderately massive ones. P67b represents the extreme end of this phenomenon in a way that is almost elegant, if elegance can be attributed to an object coming apart at the seams. A planet with less than half of Jupiter's mass inflated by the radiation of a subgiant star to more than twice Jupiter's radius. A cold planet of the same mass, the same 0.45 Jupiter masses, sitting undisturbed in the outer reaches of a planetary system, cooling quietly over billions of years, should have a radius of roughly 1 Jupiter radius, perhaps slightly less. P67b is more than double that, the same amount of gas spread across more than 10 times the volume. It is as though someone took a golf ball and inflated it to the size of a basketball while leaving the same amount of rubber inside. To understand what this does to the planet's internal structure, it helps to know what a normal gas giant looks like on the inside. Jupiter's interior, despite being composed almost entirely of gas, has a surprisingly organized layered structure. Just beneath the visible cloud tops, atmospheric pressure climbs rapidly with depth. Within a few thousand kilometers, hydrogen gas transitions from a molecular state, the familiar diatomic hydrogen molecule of chemistry classrooms, to a metallic state where electrons are stripped from atoms and flow freely like electrons in a conductor. This metallic hydrogen layer extends for tens of thousands of kilometers and is responsible for generating Jupiter's powerful magnetic field, one of the strongest in the solar system. Deeper still, at the center sits a core of heavier elements, rock iron, ice in the sense of high-pressure solid phases of water, and ammonia compressed to densities 10 to 20 times that of water. The pressure at Jupiter's center reaches approximately 40 million atmospheres. The temperature exceeds 200,000 Kelvin. It is a place of extraordinary compression, a world within a world hidden beneath thousands of kilometers of increasingly exotic matter. Now imagine spreading the material of P67b, less than half of Jupiter's total mass, across a volume 10 times larger than Jupiter occupies. Every layer thins, every pressure boundary softens. The transition from molecular to metallic hydrogen, which depends on extreme pressure, either occurs much deeper relative to the planet's radius or is greatly reduced in extent. The core, if a distinct core exists at all, sits at the center of a vastly more diffuse envelope. The pressure gradient from the planet's outer atmosphere to its center is far gentler. Instead of the sharply defined phase boundaries that structure Jupiter's interior, the molecular envelope giving way to the metallic region, giving way to the rocky core, P67b, likely has an interior that varies almost continuously, density increasing slowly from the near vacuum of its bloated outer atmosphere toward whatever modest concentration of heavier material persists at its center. No dramatic transitions, no crushing metallic shell, no fierce high-pressure core, just a smooth, gentle gradient from something toward nearly nothing stretched across a diameter larger than any planet in our solar system by a factor of more than 2. The surface gravity of this planet, the gravitational acceleration experienced at its nominal photosphere, the layer at which the atmosphere becomes opaque, is approximately 3.7 meters per second squared. Earth's surface gravity is 9.8. Jupiter's is 24.8. HATP67b's surface gravity is weaker than Earth's. A person standing on its cloud tops in a hypothetical world where such a thing were possible would feel lighter than they do on their home planet. The enormous planet exerts less gravitational pull at its surface than the small rocky world you are currently sitting on. This is what it means to be a low-density giant. The mass is spread so thin across such an enormous volume that the gravity at any given point in the outer atmosphere is surprisingly gentle, and it is precisely this gentleness, this insufficient gravitational grip that determines what happens next. Because when the gravity is this weak, and the radiation from the star is this intense, and the star is this close, the atmosphere does not stay. It cannot stay. The physics of what happens when you heat a gas beyond the escape velocity of its parent body is not ambiguous. The gas leaves. And what HATP67b is losing at this moment and every moment is not a trickle. It is a hemorrhage. A structured orbital mechanics sculpted, spectroscopically confirmed hemorrhage visible across 1200 light-years. That hemorrhage and the instruments that revealed it and the extraordinary structures it has built in the space around this dying planet come next. 1709. Claude responded, "There is a technique in astronomy that does something almost philosophically unsettling. There is a technique in astronomy that does something almost philosophically unsettling. It allows you to read the chemistry of a world you will never visit from a distance so vast that the light carrying the information left its source before our ancestors built the first cities. The technique is called transmission spectroscopy, and it works because starlight is not a single uniform beam. It is a spectrum, a continuous range of wavelengths from ultraviolet through visible to infrared, and different atoms and molecules absorb light at specific characteristic wavelengths. When a planet transits its host star, a thin ring of atmosphere along the planet's limb intercepts the starlight passing through it. Each chemical species present in that atmosphere leaves its fingerprint on the transmitted light, absorbing specific wavelengths and dimming the star slightly more at those frequencies than at others. By comparing the stellar spectrum during transit to the spectrum outside, transit astronomers can reconstruct the chemical inventory of an atmosphere they have never sampled, never touched, never come within 1200 light-years of approaching. For HATP67b, this technique did not merely reveal a list of atmospheric ingredients, it revealed a planet caught in the act of destroying itself. The first major atmospheric detection came from a team led by Aaron Bello-Arufe, using the Carmenes spectrograph at the Calaralto Observatory in southern Spain. Carmenes was designed specifically for high-resolution spectroscopy of stellar atmospheres and exoplanet systems, and it operates across both visible and near-infrared wavelengths with extraordinary precision. The team analyzed transmission spectra of HATP67b across multiple transit observations, and what they found in the data immediately signaled that this was not an ordinary atmospheric characterization. They detected sodium. This was not surprising. Sodium has been found in numerous hot Jupiter atmospheres where it exists as atomic vapor at the temperatures these planets sustain. It is one of the most commonly detected species in the exoplanet atmospheric catalog. But alongside the sodium, the team found ionized calcium atoms that have lost one of their electrons. This detection was immediately striking for a specific reason. Creating ionized calcium in significant quantities requires temperatures substantially higher than HATP67b's equilibrium. Temperature of approximately 1900 Kelvin would produce on its own. The ionized calcium was telling the observers that somewhere in the planet's upper atmosphere, temperatures were far exceeding what simple radiative equilibrium would predict. Something was heating the outermost layers of this planet to temperatures far above what the stellar irradiation alone should produce at those altitudes. The data also revealed absorption in the hydrogen alpha line and in the helium triplet, two spectral features that have become over the past decade the canonical signatures of atmospheric gas escaping from hot Jupiters. Hydrogen alpha absorption traces the presence of hot, excited hydrogen atoms in the planet's extended thermosphere. Helium triplet absorption traces metastable helium, a specific quantum state of helium atoms that forms when helium is ionized by extreme ultraviolet radiation and then recombines. Both species are found predominantly in the highest, most extended layers of a planet's atmosphere, layers that are by definition the most loosely bound and therefore the most vulnerable to escape. Their presence in HATP67b's transmission spectrum was a first indication that the planet's atmosphere was not quietly contained within some neat gravitational boundary. It was reaching outward, extending far beyond the planet's nominal photosphere, into regions where the distinction between atmosphere and escaping gas becomes difficult to draw. But the Carmene's detections, striking as they were only the beginning. A separate and independent campaign led by Michael Gully Santiago and conducted using the Habitable Zone Planet Finder spectrograph on the Hobby Eberly telescope in Texas produced results that went far beyond what anyone had expected to find. The Habitable Zone Planet Finder, known by the acronym HPF, operates in the near-infrared portion of the spectrum, where the helium triplet absorption line sits. It was originally designed to search for planets around cool red dwarf stars, but its extraordinary sensitivity in the near-infrared makes it uniquely capable of detecting extended helium outflows from hot Jupiters. The Gully-Santiago team committed a substantial amount of telescope time to HATP67b, 13.8 hours of on-sky integration spread across 39 separate nights. They sampled not just the transit itself, but the planet's entire orbit, observing the system at every phase from well before the transit to long after it. The helium signal they found was enormous, up to 10% excess absorption in the helium triplet line during transit, 10% of the total starlight at those wavelengths being absorbed by helium in the planet's extended atmosphere. For context, most exoplanet transit depths in broadband light amount to a few percent at most, even for large planets. A 10% signal in a specific spectral line produced by the extended atmosphere alone indicates a cloud of escaping helium so vast and so dense that it is intercepting a significant fraction of the stellar flux across a very wide area. But the number that truly defined the observation was not the absorption depth during transit. It was where the absorption appeared. The excess helium signal did not begin when the planet's physical disk crossed the edge of the stellar limb. It began before, measurably unambiguously before. The signal appeared while the planet was still approaching the star before the transiting body had crossed in front of any stellar surface. Something was absorbing helium light ahead of the planet, leading it in its orbit, extending forward into the space in front of the planet's trajectory. The team quantified this leading structure. The excess absorption was detected at distances extending up to 130 planetary radii ahead of the planet, 130 times the planet's own width stretched out in front of it like a vast gossamer arm reaching toward the star. If the planet itself spans approximately 3,000,000 kilometers in diameter, then the leading helium tail reaches approximately 39 million kilometers ahead of it in its orbit. That is roughly a quarter of the distance from Earth to our Sun, a structure built entirely of escaping gas invisible in ordinary light, but blazing in the specific wavelength of helium absorption, announcing its presence to anyone with the right instrument. A trailing tail was also detected fainter and less extended following behind the planet in its orbit. The asymmetry between the leading and trailing structures is not accidental. It is a direct consequence of the physics governing how gas escapes from a planet in a tight orbit. The planet's day side, the hemisphere permanently facing the star, receives the most intense irradiation. The gas in the upper atmosphere on this side is heated, most aggressively expands, most vigorously, and is most readily lifted beyond the planet's gravitational reach. When this gas escapes, it does not simply drift outward in all directions. It escapes into a gravitational field shaped by both the planet and the star, modified by the Coriolis forces that arise because the whole system is rotating. Gas escaping from the day side is launched forward relative to the planet's orbital motion sweeping ahead of the planet along its trajectory. Gas escaping from the trailing hemisphere follows a different path, curving backward. The result is a lopsided asymmetric structure, a prominent leading arm and a dimmer trailing tail, precisely the geometry that the HPF observations confirmed. The Doppler velocity structure of the helium signal provided additional confirmation that this interpretation was correct. Gas moving in an escape flow from a tidally locked planet should exhibit specific velocity patterns relative to the planet's rest frame. The observed velocities were consistent with material moving away from the planet and being shaped by orbital dynamics, not with material in a simple hydrostatic atmosphere held in place by the planet's gravity. The gas was leaving, and its velocity told the story of how it was leaving. The Gully-Santiago team also used theoretical models to estimate the rate at which the planet was losing mass. These are called Parker wind models, named after Eugene Parker, the physicist who first described the mathematics of the solar wind in the 1950s. A Parker wind model describes how a heated gas at the base of an outflow accelerates as it expands outward, passing through a critical point, the sonic point where the outflow velocity equals the local speed of sound and beyond which the gas inevitably escapes. The models are one-dimensional and involve assumptions about the temperature and ionization state of the escaping gas, the size of the planet, and the extreme ultraviolet flux from the host star. Given the uncertainties in HAT P67's ultraviolet output, the mass loss rate estimates carried large uncertainties, but the central values pointed consistently to a rate on the order of 10 to the 13th grams per second. In more intuitive units, approximately 10 million metric tons of atmosphere escaping every single second. 10 million metric tons every second. Consider what that actually means for a moment. In the time it takes you to draw a breath, this planet has shed roughly 10 million metric tons of its own atmosphere into space. In the time it takes you to read this sentence aloud, the loss exceeds 100 million metric tons. In a single day, the cumulative mass shed is roughly 8,000,000 billion kilograms. In a year, the total loss exceeds a quantity that dwarfs every structure humanity has ever built, combined many times over. The third independent observational campaign, led by Cecilia Mancini and collaborators, approached the system from a different angle. Rather than focusing on in-transit observations alone, the team analyzed spectra acquired at various orbital phases, including observations made after the transit had ended. They found a clear helium absorption signal in the post-transit spectra, a signal that persisted after the planet's physical disk had moved away from the stellar limb. This post-transit signal is the signature of the trailing tail, the stream of escaping gas following behind the planet in its orbit, briefly crossing in front of the star even after the planet itself has passed. The Mancini team also attempted to quantify the extent of the escaping gas cloud in a different and perhaps more viscerally striking way. Rather than measuring the length of the tail, they estimated the effective radius of the planet at the helium triplet wavelength, the radius that the planet appears to have when viewed in the light of helium absorption rather than in broadband white light. In broadband light, the planet's transit reveals a disk of approximately 2.14 Jupiter radii. That is the radius of the opaque photosphere, the depth at which the atmosphere becomes thick enough to block a measurable fraction of the starlight. In helium light, the planet appears to extend to a radius of approximately 6 Jupiter radii. 6. The physical planet is just over 2 Jupiter radii wide. The cloud of escaping helium surrounding it, the outflow atmosphere billowing outward in every direction before being swept into the leading and trailing streams, makes the planet appear nearly 3 times larger than it actually is, depending on which wavelength you choose to observe it in. 6 Jupiter radii. That is a sphere roughly 8,400,000 kilometers across. Our Sun has a radius of approximately 6,960,000 kilometers. The escaping atmosphere of HATP67b, seen in helium light, spans a volume wider than our own star. The Sun is a ball of gas containing 333,000. Earth masses the gravitational anchor of our entire planetary system, the source of every photon that has ever warmed the surface of our world, and the cloud of gas bleeding away from this dying planet, in this particular wavelength, is wider than it. These 3 independent detection campaigns using 3 different spectrographs at 3 different observatories, arrived at the same conclusion through different observational routes. The planet is losing its atmosphere. The loss is not a gentle trickle at the edges. It is a structured physics-driven outflow that has built coherent structures extending tens of millions of kilometers from the planet, structures with measurable velocities, measurable extent, and measurable mass loss rates. The planet is not sitting at the edge of stability. It has crossed the threshold. The process that will eventually destroy it is already underway, visible from across the galaxy to anyone pointing the right instrument at the right patch of sky. To understand why this outflow takes the specific form it does, why it builds a leading arm rather than a symmetric halo, why the gas does not simply expand in all directions and disperse, requires confronting the concept of the Roche lobe. The Roche lobe is the region of space around each body in a 2-body gravitational system within which material is gravitationally bound to that particular body rather than to its companion. It is not a sphere. It is a teardrop-shaped gravitational boundary with its narrow end pointed directly toward the companion object. The size and shape of the Roche lobe depend on the mass ratio of the 2 bodies and on their orbital separation. For HATP67b, the combination of its low mass, its massive host star, and its extraordinarily tight orbit produces a Roche lobe that is remarkably compact relative to the planet's inflated physical size. The planet does not merely approach its Roche lobe boundary, it overfills it. The planet's extended atmosphere bloated by intense stellar irradiation to a scale height of approximately 800 kilometers compared to Earth's atmospheric scale height of roughly 8.5 kilometers reaches beyond the gravitational boundary, where material can remain bound to the planet. Gas that crosses this boundary is no longer in the planet's gravitational domain. It falls under the combined influence of the planet and the star, and the dynamics of this combined field shaped by the Coriolis forces of orbital motion channel the escaping gas into specific trajectories. Gas escaping through the inner Lagrange point, the narrow gravitational neck aimed directly at the star flows toward the star along a curved trajectory shaped by the Coriolis force into the leading arm we have already observed. Gas escaping through other regions of the Roche lobe follows different paths, some forming the trailing stream, some being swept away by the stellar wind into the broader interplanetary environment of the system. The result is not a symmetric expanding cloud, but a dynamically structured outflow, a set of organized streams following the contours of the combined gravitational and rotational potential field of the star-planet system. This is Roche lobe overflow, a phenomenon astronomers had studied theoretically for decades in the context of binary star systems, where one star overflows its Roche lobe and transfers mass to its companion. For binary stars, this process can be spectacular, powering nova explosions when the transferred material ignites on the surface of a white dwarf companion, or producing the dramatic accretion disks of interacting binary systems. The same physics, scaled down from stellar masses to planetary masses, operating between a planet and its host star, is what we are watching unfold around HATP67b. A gas giant is overflowing its gravitational boundary and streaming its own atmosphere toward the star that is destroying it. The combined picture that emerges from all of these observations is one of breathtaking physical coherence. Every piece fits. The low density explains why the planet overfills its Roche lobe. The overfilled Roche lobe explains why gas escapes at such a prodigious rate. The escaping gas, shaped by orbital dynamics, explains the asymmetric structure of the leading and trailing tails. The extent of those tails explains the pre-transit and post-transit absorption. The high temperature of the upper atmosphere reflected in the ionized calcium detection explains why the escaping gas is accelerated to velocities sufficient to leave the planet entirely. And the enormous scale height produced by the combination of high atmospheric temperature and weak surface gravity explains why the transmission spectroscopy signal is so large and why so many teams have been able to detect so many species despite the planet sitting 1200 light-years away. There is a unity to this picture that is deeply satisfying in the way that good physics always is. When observations from independent teams using independent instruments arrive at mutually consistent results through independent methods, you know you are looking at something real. HATP67b is not a borderline case, a marginal detection, a planet whose extreme properties might evaporate upon closer scrutiny. It is one of the most thoroughly characterized extreme planets in the exoplanet catalogue, its strangeness confirmed and reconfirmed from every angle observers have been able to approach it. And yet, for all the coherence of the observational picture, one question has been quietly sitting at the edge of the story waiting to be addressed. We know the planet is losing its atmosphere at 10 million metric tons per second. We know the Roche lobe is overfilled. We know the destruction is underway, but the system is more than 1 billion years old. The planet has been sitting at this orbital distance from this star for over 1 billion years. If the atmospheric escape is so catastrophic, why does any atmosphere remain? Why has the planet not already been stripped bare? The answer involves the star itself and the timing of its evolution. And that answer, when fully traced, reveals that we are not merely observing a planet in distress. We are observing a planet at a very specific and very brief moment in its billion-year history. The moment when the conditions for its destruction have only just been met. 1711. Claude responded. There is a question that haunted the study of HATP67b for years before the 2025 paper finally provided the framework to answer it. There is a question that haunted the study of HATP67b for years before the 2025 paper finally provided the framework to answer it. The question is simple to state and deeply uncomfortable to sit with. If this planet is losing its atmosphere at 10 million metric tons per second, if its Roche lobe is overfilled, if theoretical models predict that planets with densities below 0.1 grams per cubic centimeter should be completely stripped of their atmospheres within less than 100 million years, then why does this planet still have an atmosphere? The system is more than 1 billion years old. HATP67b has been orbiting at its current distance from its host star for the vast majority of that time. The orbital alignment is nearly perfect, indicating smooth disk-driven migration rather than any recent dynamical disruption. The planet has not arrived at its current position recently. It has been sitting 10 million kilometers from its star for most of its existence. And yet there it is, still enormous, still transiting, still puffy, still surrounded by an atmosphere thick enough to produce helium tails extending 130 planetary radii into space. According to the models that describe atmospheric escape from low-density hot Jupiters, this planet should have been stripped bare hundreds of millions of years ago. It should be a naked, rocky core, or perhaps nothing at all. It should not exist in its current form. The resolution of this paradox is one of the most intellectually satisfying things the 2025 Wang and collaborators study produced, and it completely reframes how we should understand what we are watching. The key lies not in the planet but in the star, specifically in what the star was doing for most of the past billion years and what it has only recently started doing differently. To understand this, you need to know something about how a star's radiation output changes over its lifetime. A star is not a static object. It is a nuclear furnace, undergoing continuous structural evolution, and the nature of that evolution produces different radiation profiles at different stages of its life. The radiation that drives atmospheric escape from close orbiting planets is not the visible light that warms the planet's dayside. It is extreme ultraviolet radiation at wavelengths far shorter than visible light, carrying far more energy per photon. Extreme ultraviolet photons are energetic enough to ionize hydrogen directly to strip electrons from hydrogen atoms in the planet's upper atmosphere, creating a superheated plasma that expands outward and escapes. This is the photoionization-driven escape mechanism, and it depends critically on how much extreme ultraviolet flux the planet receives from its host star. Extreme ultraviolet emission from a star is not primarily determined by the star's total luminosity, the overall amount of energy it radiates. It is determined by the star's magnetic activity. Young stars are magnetically vigorous. Their surfaces are threaded with complex magnetic field structures, churning with convection and rotation that generates intense ultraviolet and X-ray emission. Over time, as a star ages on the main sequence, its rotation slows through magnetic braking. The star loses angular momentum through its stellar wind, and its magnetic activity declines. Ultraviolet and X-ray output drops. The star becomes radiatively quieter, even as its total luminosity may change only modestly. For an F-type star like HATP67, this evolution follows a well-characterized path. Early in the star's life, when it was young and magnetically active, extreme ultraviolet output was elevated. As the star aged through its main sequence lifetime, and its rotation slowed, and its magnetic activity declined, the extreme ultraviolet flux dropped to levels that, while still significant, were not sufficient to drive runaway atmospheric escape from the planet. The planet received intense visible and infrared radiation, enough to inflate its atmosphere to the record-breaking dimensions we observe, but not enough extreme ultraviolet to push the atmospheric escape into the catastrophic runaway regime that the models predict for such low-density worlds. For over 1 billion years, HATP67b existed in a state of precarious but genuine stability. Its atmosphere was inflated, its scale height was enormous, its density was below what any cold planet of the same mass could achieve. But the rate of atmospheric escape was slow enough that the planet could sustain itself. The outflow was a trickle rather than a flood. The Roche lobe was perhaps slightly overfilled, or perhaps only marginally so, with the escape proceeding at a rate that did not threaten the planet's survival on billion-year timescales. The planet was a balloon inflated to an uncomfortable size, pressed against a wall of heat, but not yet punctured. Then the star began to change. HATP67 has spent more than 1 billion years fusing hydrogen in its core. But F-type stars burn their fuel faster than cooler, less massive stars do. Where our Sun will remain on the main sequence for roughly 10 billion years, total an F-type star of HATP67's mass exhausts its core hydrogen supply faster. The star has been approaching the end of its main sequence lifetime, and it has begun the transition that marks that end. As the hydrogen in the core depletes, the core contracts and heats up. The extra heat causes the hydrogen-fusing shell surrounding the core to burn faster. The outer layers of the star respond by expanding. The star grows. Its surface temperature adjusts. Its luminosity increases. It has entered the subgiant phase, the bridge between the stable hydrogen-burning main sequence and the dramatically inflated red giant that will follow. This evolutionary transition changes the star's radiation output in ways that have nothing to do with magnetic activity and everything to do with the sheer increase in luminosity. As the star brightens and its structure changes, the extreme ultraviolet flux reaching the planet begins to climb. Not because the star has suddenly become magnetically young again, but because the overall increase in luminosity carries with it an increase in the higher energy radiation components. The extreme ultraviolet flux hitting the planet crosses a threshold, the threshold above which the mass loss rate from the planet's already extended, already weakly bound atmosphere accelerates into the runaway regime. The Wang et al. 2025 study concluded that this transition has occurred recently in cosmic terms, meaning within the past few 100 million years. For most of the system's existence, the planet was inflated but stable. The extreme ultraviolet flux was insufficient to drive catastrophic escape. The planet survived. Then the star evolved off the main sequence. The radiation environment shifted. The escape rate crossed the critical boundary. The runaway began. What this means is staggering in its implications. We are not observing a planet that has always been in crisis. We are observing a planet that spent more than 1 billion years in relative safety and has only recently entered its terminal phase. The helium tails, the 10 million metric ton per second mass loss, the Roche lobe overflow, all of this represents not a chronic condition but an acute one, a condition that has only recently been triggered by the evolving star. We are witnessing the opening act of a destruction that will last hundreds of millions of years, and that has only just begun. The timing of our observation is not random in the sense of being surprising, but it carries a weight that is worth sitting with. The universe is 13.8 billion years old. Our technological civilization capable of detecting exoplanets and measuring their atmospheric escape has existed for roughly 30 years. In 30 years of exoplanet observation, we happen to point our instruments at a system in which a planet has just within the last cosmically tiny sliver of time crossed the threshold into runaway destruction. We arrived at exactly the right moment to see the beginning of the end. This is the observation window problem, stated in its most visceral form. For every planet we observe in crisis, there are unknown numbers we have missed because we looked too early before the crisis began or too late after it had concluded. HAT P67b is visible to us because we exist during the narrow temporal window in which its destruction is underway, but not yet complete. Had our technological development been delayed by 1 billion years, had humanity somehow arrived at this capability only after the star had fully evolved and the planet had been consumed, there would be no HAT P67b to observe. There would be an expanding red giant star, with perhaps a bare, rocky remnant somewhere in its vicinity or nothing at all and no record of the extraordinary planet that had once orbited there. The physical conditions at HAT P67b's orbital location now that the star has entered its subgiant phase are worth examining directly to understand what the planet is experiencing in concrete terms. The host star, already 2.65 times the width of our Sun, fills an enormous portion of the planet's sky. From the cloud tops of HAT P67b, if you could somehow hover there, the star would not present the modest disk that our Sun offers from Earth. It would dominate the heavens, stretching across approximately 20 degrees of sky, nearly 40 times the apparent width of our Sun as seen from our planet. The entire dayside hemisphere of the planet is bathed in radiation, so intense that atmospheric molecules shatter into their component atoms. The equilibrium temperature of approximately 1900 Kelvin places the planet at the boundary between what astronomers classify as hot and ultra-hot gas giants. On the dayside, the atmosphere crosses into a chemical regime where water molecules dissociate, where hydrogen exists primarily as single atoms rather than paired molecules, where metals like iron and magnesium float as gaseous atomic species at altitudes, where Jupiter would have clouds of ammonia ice. The night side tells a completely different story. Tidally locked, or very nearly so, with the same hemisphere permanently aimed at the star, the planet's far side receives no direct starlight at all. Temperatures there plunge by hundreds of Kelvin, creating one of the most extreme thermal gradients in the known exoplanet population. At the terminator, the boundary between permanent day and permanent night, a thin band of perpetual twilight wrapping around the planet's equator, the temperature drops by hundreds of degrees across distances shorter than the width of a continent. Cloud species that exist only in gaseous form on the day side may condense into liquid or solid particles along this twilight boundary. Atmospheric dynamics are driven to extraordinary velocities by this temperature contrast, with equatorial jet streams reaching several kilometers per second as the heated dayside gas rushes toward the cooler night side. These dynamics are also contributing to the destruction. The same circulation patterns that redistribute heat around the planet are carrying ionized gas through the planet's magnetic field, generating the electrical currents that deposit heat in the interior through ohmic dissipation. The same high temperatures that drive the jet streams are also heating the upper thermosphere to approximately 9900 Kelvin, nearly 5 times the planet's equilibrium temperature, through the absorption of extreme ultraviolet radiation and the hydrodynamic processes of the escaping gas itself. At 9900 Kelvin, the upper atmosphere is hotter than the surface of many stars. It is a place of extraordinary thermal violence, and it is the launch pad from which the planetary wind escapes. The planetary wind analog deserves careful attention because it is the mechanism connecting all of the observations we have explored. Our Sun has a solar wind. It is produced because the Sun's corona, the outermost layer of the solar atmosphere, heated to millions of degrees by mechanisms that include magnetic reconnection and wave heating, expands outward faster than gravity can restrain to it. At some critical distance from the Sun, the outward velocity of the expanding corona exceeds the local escape velocity, and the gas flows away freely into interplanetary space, becoming the continuous stream of charged particles that shapes the magnetospheres of every planet in the solar system, and was detected by the Voyager spacecraft. Even in the outer reaches of the heliosphere, HATP67b has a planetary wind operating by the same physics scaled from a stellar corona to a planetary thermosphere. The extreme ultraviolet photons from the host star ionize hydrogen and helium in the planet's upper atmosphere, depositing their energy as heat. The heated gas expands upward, the density drops. The pressure gradient accelerates the gas outward. At the sonic point, the altitude at which the outflow velocity equals the local speed of sound, the gas becomes supersonic, and its escape becomes inevitable. Beyond the sonic point, gravity can no longer pull the gas back. It continues to accelerate outward into the space around the planet, eventually reaching the Roche-Lobe boundary and spilling into the leading and trailing streams that the helium observations revealed. The mass loss rate from this planetary wind has been estimated at roughly 10 million metric tons per second. But this figure deserves context in terms of what it means for the planet's future, because the numbers that emerge from a careful calculation are simultaneously reassuring and terrifying depending on how you frame them. HATP67b has a total mass of approximately 0.45 Jupiter masses, or about 8.5 times 10 to the 29th grams. At the current estimated mass loss rate, it would take on the order of 2.7 billion years to strip away the entire planetary mass. On that timescale, the mass loss alone is not what will end this planet's existence in its current form. What will end it is the star. HATP67 is brightening. It is swelling. As it continues its evolution through the subgiant phase toward the red giant branch, its outer layers will expand dramatically. The expansion will not be gradual in the sense of being negligible. Red giants can swell to hundreds of times their main sequence radius. Our own Sun, when it reaches the red giant phase in approximately 5 billion years, will expand to engulf the orbits of Mercury and Venus, and possibly Earth. HATP67 is already 2.65 times the radius of our Sun. As it continues to evolve, its surface will expand outward toward the orbiting planet. The Wang et al. 2025 study estimated that the planet will be tidally disrupted or physically engulfed by its host star within approximately 150 to 500 million years. The range reflects uncertainty in the rate of stellar evolution, in the precise mass loss history of the planet, and in the details of how tidal interactions between the expanding star and the close orbiting planet will reshape systems dynamics as the star grows. But the range does not include any scenario in which the planet survives, whether the atmosphere is stripped entirely before the star reaches the planet's orbit, or whether the expanding stellar surface swallows the planet while some atmosphere still remains. The outcome is identical. Within a few hundred million years, HATP67b will cease to exist as a recognizable planet. The planet is being destroyed from two directions simultaneously. From above, the stellar radiation drives the atmospheric escape that gradually erodes the mass that makes it a planet. From below, the expanding stellar surface is advancing toward the planet's orbit like a slow tide, closing the distance that has defined the system's architecture for more than 1 billion years. The planet cannot escape in either direction. It cannot move to a safer orbit. The very tidal interactions that are reshaping the system are also likely causing the planet to spiral inward rather than outward. As the star expands and the tidal coupling between star and planet intensifies, it cannot reaccrete the gas it is losing because the escaping material falls toward the star and is swept away by the stellar wind. It can only continue to be what it currently is for as long as that remains possible. And what it currently is at this specific moment in its existence, at this precise point in the star's evolution, at this particular instant in cosmic history, is the largest confirmed planet, one of the most extreme objects in the exoplanet catalogue, a world whose defining characteristic, its extraordinary inflated radius, is simultaneously the signature of its creation and the mechanism of its destruction. And it is a world that has agreed without being asked to serve as a laboratory, a real physical, observable demonstration of processes that shape the entire population of planets across the galaxy. Because what is happening to HATP67b is not unique to it. It is a magnified, accelerated, extreme version of processes that operate everywhere that planets orbit close to their stars. The radius valley, the conspicuous gap in the size distribution of exoplanets between roughly 1.5 and 2 Earth radii observed in the catalogues produced by the Kepler and TESS missions, is thought to result primarily from atmospheric escape stripping the envelopes of small, close-orbiting Belia planets. Planets that were once sub-Neptunes with thick hydrogen and helium envelopes have had those envelopes removed by photoionization-driven escape, leaving behind bare rocky cores that now populate the super-Earth category. The same physics operating on a much smaller scale and over much longer timescales has sculpted the demographics of the planetary population we observe today. HATP67b shows us that same process operating at its most extreme limit, not a sub-Neptune losing a thin envelope, a gas giant losing its entire atmospheric mass, not a gradual billion-year erosion, a catastrophic runaway outflow triggered by a stellar evolution event happening in real time. Every measurement made of this planet, every transit depth, every radial velocity, every helium absorption signal, every mass loss rate estimate constrains the physics of atmospheric escape in a regime that no other confirmed planet occupies so dramatically. It is a natural experiment that no laboratory on Earth could replicate, running at full scale across 1,2,0,0 light-years, announcing its results in the language of spectral absorption to anyone patient enough to read them. But all of these measurements, all of these mechanisms, all of these calculations about mass loss rates and stellar evolution and Roche lobe geometry ultimately converge on a question that sits beneath the science, not a question about the planet's fate which is settled, not a question about the physics of its destruction which is well characterized, but a deeper question, the one that this story has been building toward from the moment we first described a planet less dense than a marshmallow, a question about what the word planet means when the object it describes is simultaneously one of the largest ever found and one of the most temporary, one of the most physically extended and one of the most structurally insubstantial, one of the most thoroughly confirmed and one of the hardest to locate precisely in space because it blends continuously from concentrated gas into escaping stream into stellar wind with no definable boundary in between. That question, and the philosophical reckoning it demands, is where this story ends. 1714. Claude responded, "There is a moment in every great scientific story when the facts stop being facts and start being something else. There is a moment in every great scientific story when the facts stop being facts and start being something else. Something that changes not just what you know, but how you see. Not because the data shifts, the data remains exactly what it was, but because the accumulation of measurements finally reaches a critical mass and collapses inward into meaning. This is that moment for HATP67b. Because when you hold everything we have established together in a single frame, the radius, the mass, the density, the helium tail, the mass loss rate, the Roche lobe overflow, the evolving star, the 150 million year death sentence, what you are left with is not simply a description of an unusual planet. You are left with a question about what a planet is. And that question, seemingly philosophical, turns out to have a physical answer that is more unsettling than anything the measurements alone convey. Begin with the word itself, planet. It comes from the Greek planetes, meaning wanderer, because the ancients noticed that certain lights in the sky moved against the fixed background of stars, wandering through the constellations along paths that could be tracked and predicted. For most of human history, the word referred simply to a light that moved. Then telescopes arrived, and the lights resolved into worlds, each with distinct characteristics each embodying the concept of a place, a discrete bounded physical location with an inside and an outside, a surface, or at least a definable structure, something with substance. Jupiter became a world with storms. Saturn became a world with rings. Neptune became a world with winds. Even without solid surfaces, gas giants felt like places. They had character, they had boundaries, they had the quality of being a thing rather than a process. HATP67b dismantles this intuition not gradually but completely. Ask yourself where this planet is. Not its orbital coordinates, those are known precisely, but where the planet itself is physically in the sense of where it begins and where it ends. The question seems simple. It is not. In broadband visible light transit photometry, places the planet's edge at a radius of 2.14 Jupiter radii. That is where the atmosphere becomes opaque enough to block a measurable fraction of the starlight. Beyond that radius, the atmosphere thins but continues. It does not stop. It extends outward through the scale height, 800 kilometers in HATP67b's case, nearly 100 times Earth's atmospheric scale height, into increasingly diffuse layers of gas that are gravitationally bound the planet technically, but held with diminishing strength as the Roche lobe boundary approaches. At the Roche lobe itself, the binding becomes nominal. Gas at that altitude is simultaneously in the gravitational territory of the planet and on the cusp of the star's dominion. Beyond the Roche lobe, the gas is no longer bound. It escapes. It joins the leading arm, the trailing stream, the ongoing outflow that the helium observations revealed. So where is the planet? If you define it by its opaque photosphere, it is 2.14 Jupiter radii wide. If you define it by the extent of its gravitationally bound atmosphere, it is somewhat larger. If you define it by the extent of the gas cloud that absorbs helium triplet light, it extends to approximately 6 Jupiter radii. If you define it by the outer boundary of the structured outflow before the material disperses into the stellar wind, it extends to something larger, still tens of millions of kilometers in the direction of the leading arm. Each definition is physically motivated. Each produces a different answer. None of them is wrong. They are measuring different aspects of the same gradient. This gradient is the critical thing. A planet is supposed to have an inside and an outside, a region where the object is and a region where it is not. HATP67b has no such boundary. It has a center, presumably where the density is highest, and whatever heavy element core exists sits at the bottom of the gravitational potential well. Moving outward from that center, the density decreases continuously. There is no phase transition, no sharp interface, no surface in any meaningful sense. The gas thins gradually from something to nearly nothing, and then at the Roche lobe it transitions from nearly nothing to actually escaping. The planet dissolves into its own outflow with no clear demarcation between where the planet ends and where the destruction begins. This is not merely a definitional inconvenience. It is a physical reality with measurable consequences. When the 2025 study measured a mass of 0.45 Jupiter masses for this planet, that number represents the total gravitational influence of the system as inferred from the stellar wobble. But it includes gas that is currently in the process of escaping. The atoms of helium detected in the leading arm, now 130 planetary radii ahead of the planet's disk, were until recently counted as part of the planet's mass. When did they stop being part of the planet? When they crossed the Roche lobe, when they reached the sonic point of the outflow, when they were detected by the HPF spectrograph as excess absorption. The question has no clean answer, because the transition from bound to escaping is not instantaneous. It is a continuous acceleration through a gravitational gradient from slow-moving bound gas to fast-moving free stream, with every intermediate state existing simultaneously at different altitudes. The mass of this planet is not a fixed property. It is a snapshot of a process. The measurement made today is not the mass that existed 1 million years ago, and not the mass that will exist 1 million years from now. The planet is not an object with a mass. It is a stage in a process with a current mass. The distinction feels philosophical until you realize it has concrete implications for how we model the system, how we predict its future, and how we interpret the measurements we make. Consider what this does to the concept of a planetary surface. Every planet in our solar system has some notion of a surface, even if it is only conventional. For rocky worlds, the surface is obvious, solid ground, geologically active or dormant, but physically real. For gas giants, astronomers define the surface as the 1 bar pressure level, the altitude at which atmospheric pressure equals Earth's sea level atmospheric pressure. This is a convention, not a physical reality, but it provides a consistent reference point for comparing planetary radii and calculating surface temperatures. At the 1 bar level, the atmosphere is thick enough that the planet behaves in a meaningful sense like a bounded object. The material below is clearly inside the planet. The material above is clearly atmosphere. For HATP67b, even this conventional surface becomes difficult to anchor physically. The 1 bar level exists presumably somewhere deep in the planet's interior. But the relationship between that level and the observable photosphere, the radius measured by transit photometry, is complicated by the extreme scale height and the ongoing mass loss. The photosphere itself moves outward as the atmosphere expands. The reference level that astronomers use to define the planet's size is not a fixed physical location. It is a moving target, slowly drifting outward as the planet's interior thermodynamics adjust to the increasing stellar irradiation and the decreasing atmospheric mass. The planet is not just losing material, it is losing itself. Nature does not draw sharp lines. We draw them because our minds require categories and boundaries to organize experience. But the universe operates along gradients and spectra, with objects shading continuously into one another, resisting the neat boxes we construct to contain them. HATP67b is the universe demonstrating this with unusual bluntness. It is a planet. It meets every formal criterion. It orbits a star. Its mass is below the deuterium burning threshold that defines the boundary between giant planets and brown dwarfs. It transits. It has a measurable atmosphere. It appears in the NASA Exoplanet Archive with all the appropriate entries filled in. But it is also a process, an ongoing dissolution, a transition from the state of being a planet to the state of being distributed, gas occurring slowly by human standards, but rapidly by cosmic ones, beginning now and proceeding with the inevitability of physics. The formal definition of a planet adopted by the International Astronomical Union in 2006, the same definition that reclassified Pluto and generated enormous public debate, requires 3 conditions for main sequence planetary status. The object must orbit a star. It must have sufficient mass for gravity to pull it into a roughly spherical shape, and it must have cleared the neighborhood around its orbit. HATP67b satisfies all 3, but the definition was written for objects that are stable on astronomical timescales. It was not written for objects that are actively transitioning from one category to another. It was not written for worlds that are at the moment of observation in the process of ceasing to be worlds. There is a concept in philosophy of science called the Sorites paradox, also known as the problem of the heap. If you have a heap of sand and you remove one grain, you still have a heap. If you remove another grain, you still have a heap. But if you continue removing grains one by one, at some point you no longer have a heap. The problem is that no single grain removal transforms a heap into a non-heap. The transition happens gradually, and there is no principled place to draw the line. HATP67b is living the Sorites paradox at planetary scale. It loses 10 million metric tons of atmosphere every second. After each second, it is still a planet. After each day, still a planet. After each millennium, still a planet. But at some point in the next 150 to 500 million years, it will not be. And there will be no single moment of transformation, no instant at which it was a planet, and the next instant at which it was not. There will only be a continuous gradient of decreasing mass and decreasing coherence, until the word planet no longer applies by any reasonable interpretation. The universe built this object at the outer edge of what physics allows, and the price of that extremity is not merely brevity, it is ambiguity. HATP67b cannot be both the largest known planet and a stable, enduring world. The same conditions that produce the record-breaking radius are the conditions that guarantee its impermanence. The inflation and the destruction are not separate phenomena connected by unfortunate coincidence. They are the same phenomenon viewed from different angles. The planet is large because it is close to the star. It is dying because it is close to the star. Its greatest attribute and its fatal condition share a single cause. This relationship between extremity and impermanence appears throughout the universe at every scale, and recognizing it in HATP 6.7b connects this one strange planet to a much broader truth about how nature operates at its limits. The most massive stars are also the shortest lived. A star 100 times the mass of our Sun burns its fuel so ferociously that it exhausts its core hydrogen in a few million years. Our Sun will persist on the main sequence for 10 billion years. A star of 100 solar masses will be gone in less than 0.01% of that time. The most luminous quasars, supermassive black holes accreting gas at rates that make them briefly brighter than entire galaxies, represent transient phases in the lives of galactic nuclei that settle afterward into comparative quiet. The most energetic single events in the observable universe, gamma-ray bursts, releasing more energy in seconds than our Sun will emit over its entire 10 billion year lifespan, last for seconds or minutes before fading. Extremity costs time. Nature permits objects at the boundaries of possibility, but the price of occupying those boundaries is brevity. The universe can build a planet wider than 2 Jupiters, but it cannot sustain one for billions of years under the conditions that produce that width. The record holder is always on borrowed time. Among the more than 5700 confirmed exoplanets, objects as extreme as HATP 6.7b are vanishingly rare. Not because the conditions that create them are impossible, clearly they are not, but because the conditions that create them also ensure their rapid destruction. We see so few planets in the extreme inflation zone of the mass radius diagram because most of them are already gone. Every exoplanet survey that catalogues the size distribution of close orbiting planets is implicitly cataloguing a population of survivors. The planets we observe are the ones that have not yet been destroyed. The empty regions of the parameter space, the places on the diagram where we would expect to find planets but do not, are not absences of planets. They are graveyards. Regions where planets once existed and were destroyed before we could detect them, leaving no record of their presence except the theoretical expectation that something should have been there. HATP 6.7b helps us read those graveyards. By studying a planet that is currently being destroyed, we learn the rate of destruction, the mechanisms involved, the physical conditions that trigger catastrophic atmospheric escape. We learn which kinds of planets are most vulnerable, at what orbital distances around what kinds of stars at what stages of stellar evolution. We build the physics that allows us to work backward from the current population and estimate how many planets have already been lost. The radius valley, that conspicuous gap in the size distribution of small planets, tells us that atmospheric escape has already destroyed the envelopes of enormous numbers of sub-Neptunes, leaving behind bare rocky cores. HATP 6.7b tells us that the same process can operate at gas giant scales when the conditions are sufficiently extreme, when the star is sufficiently luminous, when the orbit is sufficiently tight, when the density is sufficiently low. Every measurement made of this planet is a data point in a much larger story about how planetary populations evolve over time. The helium tail, the mass loss rate, the Roche lobe overflow, the pre-transit absorption, these are not merely curiosities of an unusual world. They are inputs into models that predict the demographics of exoplanetary systems billions of years from now, and that allow us to infer the demographics of systems billions of years in the past. HATP 6.7b is simultaneously a scientific object and a scientific instrument, a world being measured and a tool for measuring something larger than itself. Future observations will refine what we already know and reveal what we do not yet understand. Hubble Space Telescope campaigns targeting the ultraviolet absorption signatures of escaping hydrogen will better constrain the total mass loss rate and the thermal structure of the outflow. The James Webb Space Telescope, with its extraordinary infrared sensitivity, We could characterize the night-side chemistry of this planet and probe the molecular dissociation boundary, where day-side atomic gas transitions to night-side molecular species. Next-generation ground-based facilities with larger apertures and higher spectral resolution will track the variability of the helium tail across multiple orbits, searching for the signatures of stellar wind interactions and temporal changes in the outflow rate as the host star continues to evolve. Every new observation of ATP67b adds a sentence to a story that science is only beginning to read. And the story it tells is not just about this one planet. It is about the nature of extremes in a universe that permits them temporarily and erases them systematically. It is about the difference between size and substance, between the appearance of power and its reality, between what a thing looks like from the outside and what it actually is when you measure it in every dimension simultaneously. It is about what happens when the universe pushes one variable proximity to a star, intensity of irradiation, weakness of gravitational self-compression to its maximum value, and lets everything else follow from the physics. What follows is a planet that is simultaneously the most impressive and the most fragile thing we have found. A world of record-breaking dimensions built from less than half the mass of Jupiter, stretched to 10 times Jupiter's volume, bleeding 10 million metric tons of itself into space every second, wrapped in a ghost of escaping helium. Wider than our sun, orbiting a brightening star that would consume it within a cosmic eye blink. A planet that is a record and a ruin simultaneously. A monument to what physics can build and a demonstration of why physics cannot sustain it. The largest planet is not the strongest. It never was. The largest planet is the most temporary. And that inversion, that size and durability are not the same. That the most extreme things in the universe are often the most precarious, that what looks like power from the outside can be fragility measured in every direction, is the deeper truth this story has to offer. What remains is only the ending, and endings for objects like this always return to the beginning, to the moment before the questions were answered, to the night sky as it appears from where you are sitting, full of lights that seem permanent and are not, full of worlds you cannot see that are being built and destroyed on timescales that dwarf everything you have ever known, to the specific patch of sky in the constellation Hercules, unremarkable to the naked eye, where 1200 light-years away a ghost in the shape of a world continues its slow dissolution into the dark. 1716, Claude responded. Return for a moment to the beginning. Return for a moment to the beginning, to the image this story opened with, a planet more than twice the width of Jupiter, bleeding 10 million metric tons of atmosphere into space every second, trailing a ghostly tail of helium across tens of millions of kilometers of void. A planet less dense than a marshmallow. A planet that should not exist in its current form, and yet does, confirmed by multiple independent teams, catalogued in the NASA Exoplanet Archive, transiting its host star with clockwork regularity every 4.81 days in the constellation Hercules. 1200 light-years from where you are sitting. You understand that image differently now. Not just what the numbers mean in isolation, but what they mean together, what they imply about the nature of the object, the nature of its situation, and the nature of the universe that produced both. ATP67b has a radius of 2.14 Jupiter radii, a mass of 0.45 Jupiter masses, a density of 0.061 grams per cubic centimeter. It orbits its host star at a distance of 10 million kilometers, completing each orbit in under 5 days. Its atmosphere extends to a scale height of approximately 800 kilometers, nearly 100 times that of Earth, and the escaping gas forms a leading helium tail reaching 130 planetary radii ahead of it in its orbit. Its host star, a subgiant 1.73 times the mass of our Sun and 12 times its luminosity, is brightening and expanding. Within 150 to 500 million years, the planet will be engulfed. Those are the facts. They are established. They are not in dispute. But facts are only the beginning of understanding. What you have now, having followed this story from the first moment, is something beyond the facts. You have the context that transforms data into meaning. You know why the density matters, because it places this planet in a region of the mass-radius diagram, where theory predicts objects cannot long survive, and yet here it is surviving, or, more precisely, here it is in the final stage of ceasing to survive, which is a different thing entirely. You know why the helium tail matters, not merely as a spectacular observational signature, but as direct physical evidence of Roche lobe overflow of a planet whose gravitational grip on its own atmosphere has been broken by the combined effect of intense irradiation and the slow brightening of an evolving star. You know why the timing matters, because this planet spent more than 1 billion years inflated but stable, and has only recently crossed the threshold into runaway destruction, and we exist at the precise cosmic moment when that threshold has just been crossed, which is either a remarkable coincidence or a reminder that the universe is large enough to contain all possible moments simultaneously, and we simply occupy one of them. And you know something else now, something that cannot be fully conveyed by any single measurement or any single comparison, something that only emerges from the accumulation of all of them together. You know what the word largest actually means when applied to a planet? It does not mean most massive. It does not mean most powerful. It does not mean most gravitationally ferocious or most likely to endure. The largest planet is a world of extraordinary dimensions, built from a surprisingly modest amount of material held in an impossible configuration by the energy of a star that is simultaneously keeping it inflated and tearing it apart. The largest planet is the most inflated planet, and the most inflated planet is the most temporary planet. Those three facts are not separate observations. They are three descriptions of the same underlying reality. This reality inverts almost every intuition the human mind brings to the concept of scale. When we think of the largest things, we think of the most enduring things. Mountains persist for millions of years. Oceans last for billions. Stars burn for billions more. The pyramids have stood for thousands of years precisely because their size, their mass, their gravitational self-compression makes them resistant to the forces that erode smaller structures. In human experience, large things last. They weather what smaller things cannot. They resist what lesser structures succumb to. Size is a form of protection. In the universe of gas giants, orbiting close to their stars, this relationship is precisely reversed. The larger the planet, the more extended its atmosphere. The more extended its atmosphere, the more easily stellar radiation reaches its outer layers and drives escape. The more easily gas escapes, the faster the planet loses mass. The faster it loses mass, the weaker its gravitational grip on the remaining gas. The weaker its grip, the faster the subsequent escape. The cycle is not stabilizing. It is self-accelerating. Largeness in this context is not protection, it is vulnerability. The record-holding planet is the most exposed planet. Its extraordinary size is not a shield, it is a target. The natural response upon confronting this inversion is to look for the exception. Surely somewhere in the universe there is a massive, large, dense and durable planet that holds all records simultaneously. That is both the widest and the heaviest and the most enduring. Surely the largest things should also be the strongest things. Surely size and power should align somewhere, and in a narrow sense they do. The most massive gas giants objects, approaching the deuterium-burning threshold of roughly 13 Jupiter masses, are indeed both massive and large and gravitationally powerful, but they are not the widest. Their very mass compresses their material so efficiently that their radius is smaller than HAT P67B's despite containing vastly more gas. The physics of degenerate matter ensures that adding mass beyond a certain point makes a gas giant denser and smaller, not larger. The maximum radius for a cold gas giant sits at roughly 1 to 1.2 Jupiter radii regardless of how much mass you add. HAT P67B exceeds that maximum by a factor of more than 2. It achieves that excess not by accumulating more material, but by having its material stretched to a density lower than any cold planet of any mass can naturally achieve. There is no object in the known universe that simultaneously holds the record for radius, mass and density in a way that satisfies the intuitive expectation that the largest should also be the most formidable. The largest by radius is among the least massive. The most massive are not the largest. The most enduring are neither the largest nor the most massive. The records are distributed across different objects because the physics that maximizes each property works against the physics that maximizes the others. The universe does not build a single ultimate world that dominates every dimension. It builds a landscape of trade-offs in which every extreme is purchased at the cost of another quality, and nothing occupies the apex of all dimensions simultaneously. HATP67b occupies the apex of one-dimension radius and pays for it in density, in durability, in the fundamental coherence of what it means to be a planet. It is the champion of a category that destroys its champions. It holds its record by the most fragile possible tenure, and it will surrender that record not to a larger planet, but to its own dissolution, as the gas that makes it large bleeds away into the space around a dying star until there is not enough left to sustain the structure that earned it the title. Consider what it required to know this. To know the radius of a planet 1200 light-years away, you needed telescopes sensitive enough to detect the dimming of a star by less than 3% automated systems capable of monitoring hundreds of thousands of stars, simultaneously follow-up observations with larger instruments to confirm and characterize the transit signal. To know the mass, you needed spectrographs precise enough to detect stellar wobbles slower than a person walking, statistical techniques sophisticated enough to separate planetary signals from the noise of a rapidly rotating star, multi-year observing campaigns combining space-based and ground-based photometry with radial velocity measurements. To know the density, you needed both. To know the helium tail, you needed 13.8 hours of integration across 39 nights, with an instrument designed for an entirely different purpose, and the willingness to look not just during the transit, but across the planet's entire orbit, searching for signals in regions of the spectrum where conventional wisdom said nothing dramatic should appear. To know that this planet is dying, that its death has only recently begun, that we are watching the opening act of a process that will run for hundreds of millions of years. To know all of that, you needed an understanding of stellar evolution, developed over a century of observation and theory mass, loss models derived from studying the solar wind and extending the mathematics to planetary scales, population studies of thousands of exoplanets that revealed the statistical patterns only visible when you step back far enough to see the whole distribution rather than any single object. Every piece of knowledge required to tell this story was built by human beings who spent their lives pointing instruments at the sky and asking what the universe was doing, who developed mathematical tools to extract signals from noise, who communicated their findings through papers and conferences and the slow institutional machinery of peer review so that other scientists could build on what they had learned, correct what they had gotten wrong, and push the understanding forward another step. The instruments that found HATP67b were not grand, 11-centimeter apertures. Coffee can lids pointed at a patch of sky in Hercules night after night, accumulating the patient data that eventually resolved into one of the most extraordinary planets ever confirmed. The telescope that finally measured its mass is a 3.5-meter instrument at Kitt Peak in Arizona, a mountain in the Sonoran Desert where the elevation and the darkness of the sky make precision spectroscopy possible. The spectrograph that detected the helium tail was built to find planets around red dwarf stars. None of these instruments was designed for this specific discovery. All of them were turned toward it by scientists asking questions that nobody had yet answered. This is what it means for a species to understand its universe. Not to build instruments so powerful that the answers come automatically, but to ask the right questions, point the available tools in the right direction, and be patient enough to accumulate the data that the questions demand. To be willing to spend 39 nights staring at a star 1200 light-years away, gathering photons that left their source before any human civilization existed, because something in the preliminary data suggested that something extraordinary might be happening there if you looked carefully enough. To find in that extraordinary thing not just a record but a lesson about the nature of extremes, about the relationship between size and fragility, about what the universe can build and what it cannot sustain. There is a particular kind of awe that belongs specifically to this discovery. Not the awe of seeing something beautiful, though this story contains beauty. Not the awe of encountering something vast, though the scales involved are beyond ordinary comprehension. It is the awe of a specific inversion, a reversal of expectations so complete that it forces the mind to reconstruct something it thought it already understood. You thought you knew what the largest planet would be. You thought largest meant most powerful, most enduring, most gravitationally dominant. You thought size and strength were synonyms, at least in the realm of worlds. HATP67b demonstrates with the authority of multiple independent measurements confirmed by multiple independent teams over a decade of observation that you were wrong. That the largest confirmed planet is also among the most fragile. That the record is held not by a fortress, but by a ghost. That the most extreme thing the universe has built in this particular dimension is also among the most temporary. This is the specific texture of scientific awe, not wonder at the unknown, but wonder at the known. At the fact that the universe has arranged itself in a way that your intuition did not predict, and that careful measurement has revealed the arrangement with enough clarity and confidence that the surprise is not a matter of opinion. The universe is simply like this, whether or not it matches what you expected. The largest planet is fragile, the most inflated world is the most temporary, size is purchased with vulnerability, and the record is always held at the edge of destruction. Somewhere in the constellation Hercules tonight, HATP67b is completing another orbit around its dying star. It takes 4.81 days. In the time since you began reading this story, the planet has shed more atmosphere than any human endeavor has ever moved, built, or displaced. The helium tail is there right now, leading the planet through its orbit, a structure wider than our sun built, entirely of escaping gas, invisible in ordinary light, but unmistakably real. The star is a fraction of a degree larger than it was when this story began. The countdown continues by the same amount it has continued every moment for the past several 100 million years since the host star first crossed the threshold into the subgiant phase and the killing became inevitable. The planet does not experience this. It has no experience. It is not suffering. It is simply obeying physics, as everything does. And the physics says that its time measured in units vast enough to contain all of human history many times over is running short. But we know, we, the small creatures on the small rocky world, orbiting the ordinary star in the outer regions of a spiral galaxy, have pointed our coffee can telescopes and our desert spectrographs at a patch of sky 1200 light-years away, and we have measured the mass and the radius and the density and the helium tail and the mass loss rate and the orbital period and the spin-orbit alignment and the chemical composition and the extent of the outflow and the time remaining. We have read the physics of a dying world from the light that left it more than a millennium ago, and we have understood what it says. That understanding is extraordinary, not because it saves the planet, nothing saves the planet, but because it exists at all, because the universe produced among all of its countless configurations a species capable of asking what the universe is made of, and then developing the tools to find out, capable of looking at a dimming star and inferring a planet, capable of looking at a spectral line and inferring an escaping atmosphere, capable of assembling individual measurements into a coherent picture of a world in crisis and comprehending what that picture means. HATP67b will be gone within a few 100 million years. The measurements we have made of it will outlast it. The understanding we have built from those measurements will outlast it. The physics we have learned from watching it die will inform our understanding of every other planet we study, every other atmosphere we characterize, every other system in which a world and its star are locked in the intimate, violent relationship that proximity imposes. The largest planet is a ghost in the shape of a world, vast and hollow and vanishing, trailing its own dissolution through the darkness of a constellation that has no name for it, orbiting a star that does not know what it is destroying. And we are here, small and brief and somehow capable of knowing all of this, watching from 1200 light-years away with instruments no larger than a coffee can lid, reading the story of a world's ending in the language of absorbed light. The darkness around that star is very large. The planet inside it is for a little while longer enormous. And the fact that anything exists to measure either of them, that consciousness emerged in this universe and turned itself toward the sky and learned to read what the sky was saying, is perhaps the most extraordinary thing of all. Not the largest planet, not the ghost, not the dying star. Us.